Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Let's we start. इस दुआ के साथ कि खुदावन मुताल तमाम आलम इंसानियत को हालिया वबा के ख़तरा से महफूज फरमाए और हम सब के लिए आसानियाँ अता फरमाए. As you know, we are studying nuclear analytical techniques, and in this regard, in previous lecture we studied different decay processes that undergo inside the nucleus of a nuclide in order to stabilize the nuclear structure, in order to adopt the formation of a nucleon which give the stability to the nucleus of radionuclides. In this regard, a radioactive nuclide actually adopt different type of ways, different type of modes of decay processes that play a key role in order to stabilize the radioactive nucleus. In our previous lectures, we studied about six different type of decay modes, like that spontaneous fission, alpha decay process, beta decay process, beta negative and beta positive, positron decay process, electron capturing process, and isomeric transition processes. So all these different type of decay modes sometime undergo individually in the nucleus, or sometime they are associated with other type of decay mode in order to stabilize the nuclides. So very important, after decay mode, when there are different kinds of radiation emitted from the nucleus, it is necessary to measure the activity of a radionuclide, that how much radiation, how much energy of the radiation emitted from the nucleus, and what type of decay process was occurred, and how much number of radionuclides undergo such decay processes in a definite time of period. So dear students, there is a radioactive decay equations that give us information about the number of disintegrated radionuclides in a particular time, and how much concentration of radionuclide converted into daughter nuclide, and how much remain intact in a certain period of time. So something should be in your mind: the radioactivity or disintegration process, conversion of one nucleus to other nucleus. It is not a specific process, but it is a random process. What is meant by random process? Random process means there is no one can judge this molecule, this nuclide will be converted into the daughter nuclei, will be converted, disintegrated, and this one not. This is totally random process. Any of the radionuclide at any time can be disintegrated. However, after a certain time of period, that is called half-life, that is called mean life, all these terms are associated with the radioactivity decay, and the expression of these terms in the form of equation are called radioactive decay equations, and they play a role in order to give information how much quickly the particular type of radionuclide will be disintegrated into daughter nuclide, and how slow one different kinds of radionuclide may be converted into daughter nuclide. So it is totally depends upon the half-life of a nuclide. So in order to study the half-life and mean half-life and activity terms, we should take some basic information. That one is a random process. Mean there is no specificity for a radionuclide to be disintegrated. One cannot tell which atom from a group of atoms will decay at a specific time. So it is totally random process. We can only talk about the average number of radionuclide disintegrated during a period of time. So in this regard, we just talk about average number of radionuclides that disintegrated in a particular time of span. So in this regard, this gives the disintegration rate of that particular radionuclide. If there is a radionuclide consists of about 100 different nuclides, and in a particular time, in unit time, for example, in 1 minute, they disintegrate 50 of these radionuclide disintegrated into daughter nuclide. It's mean half of the concentration disintegrated into daughter nuclide in 1 minute. So the half-life of this radionuclide is 1 minute. And this is also the rate. Rate mean per unit time they how much quantity, how much number of radionuclide disintegrated converted into the data nuclides. So in this regard, we would be able to judge, we would be able to calculate the rate of disintegrated radionuclides. So in order to calculate this rate, we have considered the calculation mathematically. Okay, this is a total number of radionuclide present, and after some time the total number reduced to half of its initial quantity, initial number. So the time that was taken in order to reduce this quantity to half of initial quantity, that time is called half-life. So come to the mathematically, if there is a total number of radionuclides, we have n naught number, these are the at zero time, and total number of radionuclides are this, then in a particular time, in a certain period of time, how much number of radionuclide disintegrated. So these are the disintegrated radionuclides in a particular time of span. This particular time of span, how much radionuclide converted into daughter nuclide in a some time period of time, that is directly related to the initial number of radionuclides. So if the initial number is greater, so this change in per unit time, this disintegration in per unit time will also be greater. If this number is very low, so at this moment this change will also be very slow. Okay, so by solving this equation and this rate of change of a radionuclide into daughter nuclide directly related to lambda n naught. So there should be n naught. Okay, there should be n naught. Okay, so this is directly related. Here lambda is the num n number of radioactive atoms and lambda is the decay constant. Decay constant is specific for the particular type of radionuclide. Okay, so what is meant by rate of change of delta t, a change in time or small period of time? It is known as activity. This is known as activity. So greater the disintegration rate, greater would be the activity. What actually happened? Okay, mathematically we can write it as equation 1. This equation can be written as, this term is known as activity. So putting activity is equal to lambda and naught. Okay. In this regard, we would be able to reach at this point. This is called activity is equal to lambda and naught. So by explaining this, please have a look over this nuclide. This is a nuclide which is unstable. At some time it disintegrated, it may be disintegrated, it may be decayed through beta emission, it may be disintegrated or decay through gamma radiation emission or through alpha radiation emission, so or through positron emission. So there are different mode of decay process in which our nuclide may be decayed, may be disintegrated. So if it is not disintegrated, for a moment please consider it is not disintegrated, it is stable. If it is stable, then it should be in your mind there is no such type of radiation will be emitted from this atom. So have a look over this system. Those who are disintegrated, they have disappeared from this circle, because the radionuclide which have actually disintegrated now disappeared from. These radionuclide still alive and undergo and may be disintegrated at some other time. So it's mean those who have disintegrated, they have emitted the radiation. Those which have disintegrated undergo through decay processes, they definitely emitted the beta radiation, alpha radiation or gamma radiation. So if these are radiation which are emitted by the decaying of the some radionuclides, these due to this radiation, this atom is called activity. This is called activity. So activity actually the number of radiation emitted from the nucleus, and radiation emitted in only case when some type of decay process may occur in the nucleus process in order to stabilize themselves. So stable nuclide will never show activity. Always those atom, those nuclide which emit the radiation show activity. So activity means how much radiation emitted from the nucleus, and nucleus only emitted radiation when it undergo decay process. So greater the rate of change of disintegration, greater would be the activity. So due to this reason, this term change of uh, nuclide into disintegrated daughter nuclide, these are called activity. Okay, come to this equation now. Again, this is called activity. Equation 1 is a differential equation and can be solved by proper integration. The solution of this equation leads to by taking the integration of the equation 1. So by this is a different integral sign. So in order to integrate this equation 1, we will get log nt over n naught. So this is n naught at 0 time with maximum number of radionuclide, and this is n number after some change in after disintegrated or some of the radionuclide at a certain period of time 0 to t time. So log nt divided by n naught is equal to negative lambda t by solving this equation. So in order to further solving this equation, nt over n naught would be equal to e raised to minus lambda t. So this natural log will be converted into e raised to minus lambda t, putting this value over there. So nt is equal to, by taking this value over the other side, okay, putting here. So this is nt, number of radionuclide at time t is equal to initial number of radionuclide e raised to lambda t. This is equation 3. N naught and Nt are the number of radioactive atoms present at time 0 and time t respectively. In terms of activity, the equation can be written as At activity at time t is equal to activity at time 0. So what is meant by activity at time 0? Because at time 0 no radionuclide disintegrated, so activity will be minimum. Okay, but at time t it would be disintegrated. Most of the element, most of the radionuclide have disintegrated into the daughter nucleide and also have emitted the radiation. So activity is directly related how much the radionuclide actually disintegrated into the daughter nucleide. So this equation can be replaced by this equation in terms of activity. This graphical representation of the above equation are given in figure. If we see here, this is activity at time 0. Maximum activity is at here when time is 0. As one half-life of the radionuclide passes, this is first half-life. So after first half-life, the activity, this is the activity of a element. So this activity was reduced. So how much? This was the radionuclide that have emitted the radiations. So huge amount of activity was liberated in first half life. But in second half life, if there is like that, this is second half life. So this span is less. So after second half life, as the number of radionuclide reduced to half, in so there are initial 100. At this thereafter passage of first half life, there are only reduced to 50 nuclide, and up to other second half life from here how many nuclide will be disintegrated? Only 25, because here are 25. From here to here 25 radionuclide uh, have been disintegrated, but from this point to this point how many radionuclide was disintegrated? 50. So let's consider there are 50 radiation was emitted. Okay, because 50 radionuclide was disintegrated in first half life. In second half life, from here to here, there are other 25 radionuclide was disintegrated, and there are 25 radiations were emitted. So what do you think? In first half life, active how greater activity was appeared, or in second half life? The answer is very simple. There is in second half life the activity is less as compared to the first half life, because in first half life 50 in average 50 radionuclide was disintegrated, and in second half life there are only 25 radionuclides was disintegrated. If we consider in a third half life and undergo third half life, so there are only this is the span, and this is 12.5. So there are 12.5 radiations were emitted. So further activity was reduced. So in this regard, after each passage of each half-life, the activity of the radionuclide decreases quickly, and at after passage of four and fifth half-lives, the activity come to very minimum value. So, so we calculate half-life in terms of mathematical terms. So let number of radionuclides that was converted into daughter nuclear time t is equal to n naught e raised to minus lambda t. So this is the equation that we have mathematically derived in the previous slide. So if after t half, if this time is half life, so after passage of time, half of the radionuclide have been converted into daughter nuclide, so the T is called half time. So half of the concentration after passage of half life. So putting the value of this is here, n naught over 2 is equal to n naught e raised by minus lambda t half. Putting this t half. So this in this way, this would be cancelled with each other, and we would be able to get 1 divided by 2 into e raised to minus lambda t half life. Okay, then 2 would be equal to e raised to power lambda t half. So this negative will be cancelled with these reciprocal terms. So converting this into log term, log 2 would be equal to lambda t half. As exactly as we shown in previous slide, this log converted into e, natural log, and raised to power minus lambda t. So similarly, we do this as here. So log 2 is equal to lambda t half. Log 2, lambda was putting on this side, okay, by this, and there is half life. Okay. The value of log 2, the value of log 2 is equal to 0.69. So dear students, putting the value of log 2 here, so it would be half life is equal to 0.69 divided by lambda. So actually the half life associated with the decay constant reciprocal to the decay constant of our radionuclide. So what is the role? It should be in your mind. If the lambda value decay constant is high, it's mean the half-life would be shorter because it is inversely related to half-life of any radionuclide. And if it is lambda decay constant is have a smaller value, then half-life of a radionuclide would be greater. It's mean those who have less decay constant value are stable in nature, and those who have highest decay constant, they are less unstable. So mean decay constant mean tells us about the stability of the radionuclide. So come here please. This is the point when half of passage of half time, the concentration of from initial concentration reduced to half, that time is called half lifetime. So every radionuclide is characterized by a half-life. Lambda is equal to 0.693 divided by half-life. To determine the half-life of a radionuclide, its its radioactivity is measured at different time interval and plotted on semi-logarithm paper, resulting in a straight line as in figure 2. The slope of the straight line is one from which the half-life is determined by equation 5. Thus, the radioactivity at time t can be calculated from the initial radioactivity A naught by A t is equal to A naught divided by 2 raised to power n. So in this regard, we will be able to calculate the activity at different after the passage of different half lives. As we have carried out in previous graph, this is actually the formula that we have studied there. And this is the formula exactly like putting the second half life, it would be A divided by 4. Third half life, it would be A divided by 8, and fourth half life would be A divided by uh, 16. So this is like that. So come to another where terms that is associated with the radioactivity decay process, that is mean life. So if we see, this is the initial number of radionuclides after passage of some time. They are after passage of one half life. The radionuclide number of radionuclide going to reduce first half, and after further second half life, passage of second half life, and other reduction of radionuclide was carried out to half. So one thing that should be in your mind, these are the radionuclide that was present initially. So it's mean it is not necessarily after passage of first half-life all the radionuclide will be disintegrated. Now it is a totally random process due to which it is not specific one which that this one will be disintegrated and this will not disintegrate, but it is totally random process. However, it depends on the number of radionuclides. Greater the radionuclides number, greater would be the disintegration rate, and less the number of radionuclide, less would be the disintegration rate. However, this is a mean life. Mean life somewhat greater as compared to half-life, because if we see about here, this radionuclide, this radionuclide, that is like this, and this is present from first half, that is present at initial time to, at time when time is equal to 0, and also present at here. So it's mean it is not disintegrated. If we see about the life of this radionuclide is more than two half-lives. So some of the radionuclide was disintegrated, disappeared. That, for example, between these two, this is one, and it is not present now here. It's mean it was disintegrated. And why not this? This was not. Why not disintegrated? So this is totally random process, not depending this one. All the radionuclide will be disintegrated. So due to this reason, we can say that mean life is always greater than as compared to the half life. So what is how we can calculate mean life? So mean life is equal to total lifespan of all the atoms divided by total number of atom present. So total lifespan of the of all the atoms. So this is at zero time. I'm just discussing with you the this is time zero for your information and understanding. This is time zero. Okay, and at this time, this is time t2, this is time t1, and now further was come here only 1, 2 or 3. So this is time t3, and further this is time t4, and further, so this is t t5. So total time span mean from here to here, how much time was taken from here to here. This is a total span of total lifespan of all the atoms divided by total number of atom present, and how many total number of atom was present there. So this was uh, can be mathematically calculated with the help of mathematical equation, that is at time 0 time and dn, and the equation like that we have studied previously for. So this is 0 time to infinity time, and what change actually occur in the radionuclides divided by n0, n initial value of number of radionuclide at this time, and when there is no, this is 0 number of radionuclide. So how many time it will take in order to do this thing. So this is the total number of atom, this is the total number of time of all the radionuclide when radionuclide appear to 0. So how much time was taken, and when this number was total number of atom, how many atoms were there in for the disintegration process is equal to 1 by lambda. So the total, if we calculate and get the solution, it is equal to 1 by lambda. So mean life is equal to tau is equal to 1 by lambda. So we know that half life is equal to 0.69 divided by lambda, as we have studied in previous slide. So t half is equal to 0.69, 1 by lambda is equal to tau. So putting the value of 1 by lambda here, so it is just tau. Tau is equal to half life divided by 0.69. So if we get another value 1 by 0.69, so it is equal to 1.45 half life. So mean life actually the 1.4 times of half life. So mean life, it is the 1.45 times of the half-life. So in one mean life, the activity of the radionuclide is reduced to 37% of its initial value. Okay, let's see this figure again. So this is a activity graph which shows the activity at after each half passage of half-life, as we have studied earlier. So let's explain it. There are two kinds of radionuclides. One is with having a lambda 1 decay constant, other is a lambda 2 decay constant. Okay, if the decay constant is greater, this radionuclide has greater decay constant and this is less, so it's mean which have greater decay constant, and first this that will show less radioactive half-life. As we studied in earlier, go to previous slide, come to here, yes. Okay. So half-life is inversely related with the lambda decay constant. Greater the lambda, lesser would be the half-life. Greater the decay constant, it mean greater decay constant value mean very rapidly the radionuclide undergo decay process. But if decay constant value is less, it's mean it undergoes slowly to disintegration process with a greater half-life. Okay, again come to the point. So which have greater decay constant rapidly disintegrate. So it is rapidly, so the number of radionuclide very rapidly going down. But those with the decay constant, larger value of decay constant as compared to the first one, it not undergo very rapidly, because if we see here far up, okay, if we see this first half life and we approach to here and this here and on y-axis here. So this is reduction of a total number of radionuclide from and 0 only to this point comes here. But in case of if decay constant is greater, due to this reason, the activity is greater, as well as the disintegration of more and more radionuclide will be disintegrated, and the number of radionuclide reduce too quickly. But in case of so in opposite to this, if there is a decay constant is greater, the half-life would be less. Decay constant is greater, the half-life would be less, the half-life would be greater. Okay, so similar, you can convert this value into activity terms. So activity term will be appear like this. This is unit of radioactivity. There are different type of radioactivity unit that are using in order to express different kinds of activity. After disintegration rates, 1 curie is equal to 3.7 into 10 raised per 10 disintegration per second. So 1 curie mean 3.7 into 10 raised per 10 radionuclide disintegrate in 1 second. So such type of radiation that emitted due to the disintegration in 1 second of such number of radionuclide actually equal to 1 curie. Similarly, these are the smaller unit of curie, millicurie, and microcurie. As a unit is becquerel, so 1 becquerel is equal to 1 disintegration per second. So that is equal to 2 raised to power 7, 10 raised to power minus 11. So keep in your mind with all these there is a negative sign. There also negative sign, there also negative sign, there also negative sign. So these are the big units, larger unit of megabecquerel and terabecquerel. Similarly, 1 curie is equal to 3 point, as you know, as 1 disintegration is equal to 1 becquerel. So 1 curie should be equal to 3.7 into 10 raised to 10 becquerel. In place of this, we can put becquerel. Okay. So similarly, we this is equal to giga 10 raised by 11. So 10 raised by 11 mean giga. So this would be 37 gigabecquerel. So 1 millicurie is equal to 3.7 into 10 to the 7 becquerel is equal to 37 megabecquerel, like that. Okay, 1 microcurie is equal to this kilobecquerel. So these are the units which are frequently used in order to express radioactivity, in order to study nuclear science as well as nuclear analytical techniques. So dear students, these radioactivity units and concept of radioactivity equations should be in your mind in order to further study of radio analytical techniques. Let's see in next lecture. Allah Hafiz.